Yes, welcome you all for another beautiful presentation on field effect transistor FET, right? Field effect transistor, that is simply identified as or represented as FET, field effect transistor. This can also be sometimes can be denoted by either FET means FET are also denoted with JFET, that is JFET means JFET means it is junction. This is called as junction field effect transistor, right? Field effect transistor, right? Field effect transistor. As I already explained you in our earlier presentations that this is the another type of transistor, right? FET is the another type of transistor. So if you can recall, if you can go through our previous presentations, there I have explained you what are the types of transistors basically. So if you see what are the types of the transistor or classifications, there I have mentioned you is that the BJTs, that is bipolar junction transistors, and the second category is FET, okay, and the third one is UJT. This is UJT, right? So this is BJT, bipolar junction transistor, and this is field effect transistor. UJT is nothing but unipolar junction transistor basically. These are the three variants or three classifications of transistor, right? Again in BJT we have very clearly we have seen in our previous presentations what is a BJT and what are its configurations and what are the types of amplifiers that we have seen, and biasing techniques also we have seen. In this presentation I would like to explain you about the second classification of transistor, that is called field effect transistor. So if you see the equivalent circuit or the electrical equivalent circuit of FET, it is something like this. It is denoted by the symbol something little bit different than our BJT. Let us see clearly. So this is the representation, whereas if you see the BJT, that is something different, whereas if you see the field effect transistor, this is the representation actually. So again it is a three terminal device. This is one terminal, this is the another terminal, this is the another terminal, right? Clearly observe here, and this particular terminal I can represent the arrow mark like this. If I put the arrow mark like this, the same can also be or equivalently, if you see the same figure, I can represent like this also. This arrow mark I can show here also, right? So what is this actually? So this is nothing but drain terminal. This is called drain. This is called drain and denoted by the letter D. This is one of the terminal, and this is what actually, okay, source terminal, and denoted by the letter S, and obviously this particular is the third terminal, that is gate, denoted by the letter G, right? So this is what the basic electrical equivalent representation of a FET, right? So this arrow mark indicates the flow of electron, the flow of current, right? So this is called N channel FET. This is called N channel. This is called N channel FET. N channel FET. If you represent the arrow mark in the forward direction, this is called N channel FET. So basically, and similarly here also, instead of representing the arrow mark here, I can equivalently represent the arrow mark in the source terminal also here, the forward direction. Okay. So the same here, the terminal names are same. It is drain terminal called as D, and this is gate terminal and denoted by the letter G, and this is what the source terminal, right, and denoted by the letter S. Obviously the same, only the difference is that representation or showing identification or representation of the arrow mark either here or otherwise here, both are same, both are the same. This is what, if the arrow mark is represented in the forward direction, this is called n channel FET. So this is the n channel FET, or otherwise you can represent like this also. So by seeing this particular simple representation of the FET, you can say that the FET or field effect transistor is also a three-terminal device, a three-terminal semiconductor device. So namely, what are those three terminals? Drain terminal, and then source terminal or gate terminal, or you can write source, gate and drain, or otherwise drain, gate, source, likewise. So these are the three terminals actually of n channel. This is called n channel FET. Similarly, you can represent the same for the p channel also. So what is the p channel? Basically in FET you can have two classifications, that is n channel FET and then p channel FET, right? This is what the n channel. What is a channel? That I will explain you a little bit later, right? Now for p channel FET, for p channel, or otherwise before going to p channel, let me explain you about the what are the currents actually. So as in the case of BJT also, in BJT we have three terminals. What are those three terminals? That is collector, base and an emitter. Is it not? Collector, base and an emitter. As in the same way, here also we have three terminals as I have shown here. So as it has three terminals, the respective current will also flows through these terminals. Is it not? So in the drain terminal, so there is a current that is called drain current ID, that is denoted by the current I suffix D, nothing but drain current. So that is the current flowing through the drain terminal. Similarly, so through this gate terminal, the current flows is called as gate current, right? I suffix G, nothing but gate current. Similarly, the current flows through this source is called as IS, means source current. This is called as source current. Therefore, as we have three terminals, likewise, as we have seen in BJT, here also we have three different types of currents. So, drain current, gate current, source current, right? Here also the same. So, the current is called ID, I suffix D. This is I suffix G. This is I suffix S. Clear? So, this is what the flow of currents, right? Similarly, now coming to the p channel FET. So p channel is nothing but everything is same. Everything is same. So everything is same. Only the difference is that wherever the arrow mark is there, you just reverse. You just represent, you just identify with the reverse arrow mark. So this is the arrow mark, you can represent by reverse arrow mark. Likewise, in reverse direction. And similarly here also, so you can draw the same by showing the reverse arrow mark. So if you represent the arrow mark in reverse case, as in reverse, then it is called as p channel FET. P channel FET. Is it not? P channel FET. Otherwise, the everything is same. The representation of the symbol is the same and the terminal is also same. The current also same. Only the thing is the arrow mark only that differs. Okay, in n channel it is a forward direction, the arrow mark is in forward direction, whereas in p channel the arrow mark is reverse direction. This is the basic, this is what the electrical equivalent representation of n channel FET. Similarly, if you see the physical construction of a FET or n channel FET or p channel FET, whatever it is there, physical construction, right? So if you see the physical construction, of say n channel FET, the physical construction of n channel FET. So how the diagram or how we can represent the physical construction of a n channel FET. Let us see. It is, let us see, I will explain you the diagram actually. Let us see. Basically, it is a semiconductor bar actually, a piece of semi n channel, n type silicon, otherwise n type material will be taken first. It is a semiconductor bar of n channel. So this is a semiconductor with n type semiconductor, otherwise n type semiconductor bar. It is a n type semiconductor bar actually. Okay, and then here you can take two terminals. This is something metallic contacts actually. So from this metallic contact, one terminal is taken out like that, and here also another terminal is taken out. This is called your drain terminal, right? So this is called your source terminal. Yes, and then here also, here basically some portion of here, small portion on the both side of this n type is doped with p type material actually. This is purely this entire part, whatever you are able to see here, this entire part is a n type semiconductor. Okay, upon this entire semiconductor, within a small area, let us say this part, whatever I have shown you here. So on both side actually, on this side as well as on the right side also, this much, in this much portion of this area, it is doped with p type material, right? And from here, so one terminal is taken out. This is basically, it is called as gate 1. This terminal is called as gate, and whereas similarly from the right side also, the one terminal is taken out from here, that is called as gate 2. In general, so two gate terminal will be there in general if you see. And so as it is quite good enough to have only one terminal of gate instead of having two. That's why what we will do normally is that the second gate terminal is connected with the first one only. Means that what, both the gate terminals will be tied up, and now a single terminal is taken out, and this you can call it as gate terminal simply. Now there is no gate 1, there is no gate 2. The second gate terminal will also joined or tied with the gate 1, and now you can call it as a simple one terminal as gate terminal. Now you can consider it as a gate terminal. Is it not? Right? Is it not? That is what the physical construction. This is the n channel actually. This is what the n type material. In the n type material, with okay, with in this small portion of the area, so the doping process will be done with p type material, right? So then with from this portion actually, the one terminal will be taken out. That is called as gate 1 as well as gate 2, and it is tied up like this. And now in between these two, let us say in between these two, between gate to source, actually some voltage will be given. This is called something VGS. Normally the negative voltage is applied here. Negative voltage will be applied here, and between drain to source also, so some voltage will be connected like this. This is called VDS. So right, so from this VDS, because of this voltage between drain terminal to source terminal, some current flows through this, that is called ID, drain current. And the drain current flows through here, and this current flows from VDS to, it goes through this drain terminal, and then it flows through this area, and it will flows like this actually. This is what the flow of current in the circuit, right? It will flows like this. Initially when the VGS is very low, then you can have the This is called channel actually. From this terminal to this terminal, the area whatever is there, this is a channel actually. This is the path. This is the path actually. Through this path only, the drain current will flows through this in a circular like this. Otherwise, it's not a circular, but it will flows in this way. This is what channel actually. This is what the channel or path. Right? Right? As the voltage you will increase here, the gate to source voltage. If you go on increase this voltage, then obviously what will happen, you know? Whereas, so this is the p-type material. P-type material is obviously positive, no? P-type material is nothing but basically it is a positive. P-type material. N-type is nothing but electron. Electron is a negatively charged. Therefore, the sign is negative. Whereas for P-type material, it is a positive. So, for this positive terminal, we are applying the negative voltage here. Means that what kind of bias we are applying here? Reverse bias. Therefore, between gate to source, we are applying the reverse bias. So, this is the reverse bias voltage. So, if you increase the reverse bias voltage from slowly 0, -1, -2, -3 like that, because it is a reverse bias, so this can goes on -0, -1, -2 in the order of like that, -4 like that. If you go and increase these voltages, then obviously, so this is the p-type material doped with the n-type. Obviously what will happen, you know, this is the area between p-type n-type material to p-type material. So here it is a junction, basically it is called a junction here. This is also junction. That is what the name junction field effect transistor. This is a junction like your PN diode. It is like a PN junction diode only, right? So this portion indicates the junction actually, right? So if you increase the reverse bias voltage here, what will happen to the depletion layer? This is the junction. What happens to the width at junction in reverse bias condition? The width will increases actually. The width will increases. So means that what? So if you give -1 volt, little bit width will be increased here on both side, because the second gate is also tied to the gate 1. Therefore, on both side of these junctions, if you increase this reverse bias voltage little bit, let us say -1 volt, the width will be increases slowly. And further, if you give -2 volt here, means you are increasing here, then obviously it will increase further little bit more. And if you give -3 volt, means you are increasing the reverse bias voltage, it increases little bit more. And as you go on increase, this width will go on increase here. It will go on increase. Finally, what will happen, you know, as you go on increase this reverse bias voltage, because of the reverse bias voltage, so the depletion width will be increases finally. So this width will blocks the channel here. So this width, the depletion width or the width here, it blocks the channel. So your channel will be blocked at particular voltage of VGS, reverse bias voltage. So at which the flow of drain current becomes 0. Then you can say your ID will be 0 actually. Your ID will be 0. Means that what? The current will become 0. When? As you increase the gate to source voltage maximum, at certain maximum value of the gate to source voltage, your drain current becomes 0. Means that what? There is a very important point to note down. What is that, you know? So means that, so my current should flow through the circuit or through this particular element. So my current should flow. It should not be 0. ID should not be 0. Means you should have some value or whatever the value, but it should not be 0. When it is possible? When it is possible? So if you want to have certain value of this current ID, then you must have your VGS must be 0 as minimum as possible. So VGS must be minimum or minimum. If it is minimum, then you will get the maximum value of current. Or if it is maximum, then you will get 0 value. That is the relation between these two. I hope you understanding the well. You are following the concept. Clear? Right. So, okay. I think I will finish off this presentation here, and in subsequent presentation, we will continue this. Okay. I hope that you understand this concept very well. If so, please give your observations and comments, and do not forget to forward or to share this information to your friends, right? So we'll meet in the next presentation. Have a beautiful day till then.